kindly request the speakers of session 2, Dr. Alok Awasthi, Dr. K.K. Singh, Dr. Ebin Masto, Dr. Kartikeya Kumar Yadav, Dr. Shivendra Sinha, and Dr. Anurag Meshram to kindly approach the dais and upload their PPTs. We hope you all have a feasty lunch. We'll see you after. Thank you so much. We request you all to assemble in the hall and...
Welcome back, everyone. We hope you had a feasty lunch. We now begin session 2, titled Innovations in Recycling and Metal Extraction. This session focuses on advanced processes and emerging technologies aimed at sustainable recovery of critical metals.
To lead this session, we have Dr. Deependra Singh. Dr. Deependra Singh formerly served as the Chairman and Managing Director of IREL under the Department of Atomic Energy. With over 3 decades of experience, his expertise encompasses strategic corporate planning, R&D, project production management, and quality systems. He has also held prominent leadership roles, including President of the Rare Earth Association of India and Chairman of IIM and CAPEXIL committees.
Joining him as the co-chair is Professor Rajasekhar Reddy Sir, Assistant Professor, Department of Fuel, Mineral and Metallurgical Engineering, IIT ISM Dhanbad. His research expertise include resource recovery, thermochemical conversion, pyrolysis and gasification of renewable and non-renewable fuels, life cycle assessment and techno-economic analysis, coal beneficiation, coal to valuable minerals, waste diversion, intensified microwave reactor technology for thermochemical conversion.
Please welcome them with a round of applause. We now request Professor Shatrughan Soren to kindly felicitate our chair and co-chair with the floor to begin. Thank you so much, sir. We will now commence with session 2. Thank you.
Good afternoon. I hope everyone enjoyed the lunch, and now we are commencing the second session on innovations in recycling and metal extraction. So the first speaker is Dr. Alok Awasthi, who is the head of MP and CED Materials Group, BRC Mumbai. With his capacity, he has amassed over 35 years of experience specializing in pyrometallurgy of less common metals. He earned his bachelor's degree in metallurgical engineering from University of Roorkee, which is now IIT Roorkee, in 1988, and is an alumnus of the BRC training school. Dr. Awasthi completed his PhD from Kyoto University through the JSPS Kaku Fellowship, Japan. So, Dr. Awasthi, this is your start time, and total time is 20 minutes. Okay. So, sincere request to adhere to the time.
Right, sir. So, thank you very much, Dr. Singh. And I take this opportunity to thank the organizers, IIT ISM Dhanbad, my colleague Dr. D.K. Singh, and other youngsters who have taken very good care of us. So my talk will be somewhat different in the sense that I am a metallurgist and I work on preparation of metals, means conversion of metals to conversion of minerals to metals. And I come from atomic energy. Do you have any? Okay, so I'll continue. I come from atomic energy, and in atomic energy, we are accustomed to lean ores. Like Indian uranium ore contains only 300 ppm of uranium. In the world, perhaps the average is 1% or so. Perhaps I should not be speaking before Dr. Verma and my colleagues of AMD. They know better than me, but this is what I understand, that our ores are quite lean, and Indian Atomic Energy Program is started with very lean ores. As Dr. Saraswat also told yesterday, that Dr. Bhabha wanted to extract uranium in any case, and he had a vision for nuclear power program. So, Dr. Tiwari told about extraction of thorium occurring together with many other elements, critical elements. So this is how your Department of Atomic Energy started working in critical minerals or metals. Dr. D. Singh is here. The entire program is started from Alway plant of IREL, and because we had to extract uranium at very low concentrations, and also afterwards, as you now know, that uranium and plutonium is to be separated. After you burn uranium, it becomes plutonium, and then this plutonium is to be extracted from remaining uranium. So this is how Atomic Energy Program is started, and we are quite comfortable in separating metals or elements which have almost similar chemical properties. And then many other metals have started, like niobium, tantalum, they also occur together, zirconium, hafnium. Perhaps those who are metallurgists, they know that hafnium impurity is not tolerable in zirconium, which is to be used in nuclear sector. Even ppm level of hafnium is not permitted, but they have chemically similar properties. So this is how we started. मैं नीचे आ जाता हूँ. Okay, no issues. Okay, so these are the elements with which nuclear people are quite comfortable. So this is zirconium, hafnium, niobium, tantalum, molybdenum, rhenium, tungsten, vanadium, titanium, and of course rare earths. When I talk about these metals, zirconium, hafnium, in any case they are used in nuclear industry, but niobium, molybdenum, etc. When I say, I'm not talking about ferroalloys, I'm talking about just molybdenum without any iron content. So we were comfortable, and the extraction of these metals began in BRC in mid-60s. And now this slide I have kept because at world level, very few literature exists on such critical metals. And most of these books are, whatever are available, they are from Bhabha Atomic Research Center. Dr. C.K. Gupta was our senior colleague, and he retired some 25 years ago. So these are the books by him: molybdenum, niobium, rare earths. This book has come in second edition, vanadium, and many others. And perhaps those who are metallurgists, they must have studied the book by Professor H.S. Ray, Professors H.S. Ray, Sridhar, Abraham, Principles of Non-Ferrous Extraction. Most of the things covered about non-common, non-ferrous metals. are from, they have taken BRC's work that is quoted there. And that book was published in early 80s, I guess, and it is still continuing. Recently, I think if someone is there from BHU, Professor Shamsuddin's book is there, and afterwards perhaps no book is there in extraction of metals. Now, we know that the ores are quite lean, and these are to be concentrated, and they occur together with the elements which have similar properties. So you bring them to solution and then process them with solvent extraction and all. Means you employ complex metallurgy, rather complex chemistry, and then the metals are separated. And once the metal is separated, you have pure oxide, and then if you have to convert them to metal, then the pyrometallurgy work starts. Now the thing is, whether you are beginning with primary metal or secondary metal, when you have to convert it to metal, then you have a simple compound, usually oxide, which is quite concentrated. And then I noticed that many people think that that is the end of the job. Conversion to metal is quite easy. So that may be the case for common non-ferrous metals, ferrous metals. Of course, that is not easy. Is what I mean is that technology has matured, and as far as the common, as far as non-common, non-ferrous metals are concerned, most of the critical metals, as defined by the critical mineral missions, they fall under these categories. So, unlike common metals, these metals are quite reactive. They require high temperature, and so they may have high melting point. Usually metallurgists are comfortable with steel making, which requires temperatures of up to 1600 degrees Celsius, and the technology is quite mature. But many of these metals may have very high melting points, and then the contamination from container also may come, and as well as from atmosphere. And the variation in quality may happen from batch to batch, not from batch to batch, but from piece to piece. And even in the single piece, there may be variation from top to bottom. So this is the periodic table of elements, and the lanthanides, they are here, and besides the lanthanides, these metals are also quite reactive, and most of them are included in the definition of critical metals. Lithium, beryllium of course is used in atomic energy, sodium also in atomic energy, magnesium, calcium, scandium, and rare earths. And amongst the refractory metals, titanium, zirconium, hafnium, vanadium, niobium, tantalum, and these metals are there. So these metals are highly reactive, and you have to understand why metals behaves, or why a compound or a chemical species behave in the manner in the manner it behaves. You should be quite clear why it is behaving like this, and at the same time you have to develop the technology fast. The technology should be stable, and there the time matters. It should not happen that you keep on experimenting and the technology is not maturing. Dr. D. Singh used to tell us that we want a technology that is mature. They don't want, the industry doesn't want to do R&D. You quickly develop technology which is mature, which gives results, and which is profitable. So actually I am happy that this is the only department of metallurgy in India perhaps which doesn't have materials. I was discussing with Professor Kumari this morning that most of the IITs have converted their metallurgical engineering departments to materials and metallurgical engineering, and emphasis is more on materials, not on extraction. And then the emphasis on extraction also is mostly on hydrometallurgy. Hydrometallurgy has quite matured, but I noticed that pyrometallurgy is quite wanting in the country, and the audience has students, research scholars, industry people, CSIR laboratories, so they have to rise to the occasion, I guess. Perhaps this is the time. So most of the engineers know that a spontaneous process can occur if the entropy decreases. If by any change the entropy of the system decreases, then that process will happen. So when we talk about chemical reaction, then the species themselves and as well as their surroundings, they form the system, not alone the species. So then the concept of free energy comes, and then the reaction will occur only if delta G of the reaction is negative. This comes from the second law of thermodynamics. Stopped again. So this is the Illingham diagram of oxides. Most of the people perhaps know. And I was see what happens in this diagram is that the relative stability of oxides is plotted. At the bottom you have the calcium. Please put it full screen. Pointer pointer. Okay, it is not working. So at the bottom you have the calcium and then aluminium and like that. And this is the red one is the carbon monoxide line, carbon dioxide line, and this is carbon monoxide line, which is drooping. So the metals which the oxides of which are above the carbon, that humanity has processed and they have converted to metal. See at the top of this diagram you have precious metals like silver, palladium, titanium, etc. They are quite easy to convert to metal, just you heat and they will get converted to metal. But other metals cannot be just reduced by carbon at temperatures lower than say 950 degrees Celsius. Above the temperature above that is difficult to achieve in practice, and so these are the common metals. This is what I understand, that copper, cobalt and metals like that are common, mercury, but other metals are difficult to treat because they will get oxidized. We have the atmosphere in which oxygen is there, and when the earth formed and then most of the metals cannot exist as pure elements in atmosphere. So, and again, because scientists are here from CSIR laboratories and research scholars, please note that the Illingham diagram is very primitive way of dealing with extractive metallurgy, particularly of less common metals. So, it doesn't happen that you just reduce the niobium pentoxide and it will become niobium. It has to follow the phase diagram. From NP2O5 it becomes NbO2, then NbO, and then Nb. Similarly, I'm not able to read what this is. This is perhaps europium. So europium also has oxides. The removal of oxygen will occur through steps, and these relative oxides will form first. And it may so happen that the original oxide has lower melting point, later the lower oxides may have higher melting point. So like that you can, you have to think, and you can design the process in such a way that it works with minimum number of experiments. So this is as far as reduction under atmospheric conditions is concerned. But if you can do the reduction of an oxide under vacuum, then you have this advantage. Delta G becomes delta G naught plus RT ln Pg2, and then you get this advantage, and many reactions which are not feasible at atmospheric conditions, they become feasible. I was happy to see a poster by NML outside. They tell about navim and tantalum. Are they there? Anyone from NML whose poster is there outside? Okay, good. So you have written that navim pentoxide and tantalum pentoxide can be reduced to metal. So do you know whether this conversion is under vacuum or directly at atmosphere? So that will not work. So this is where you have to understand the science, and I'm quite happy that you have taken an initiative. Like iron, you just have Fe2O3 plus C gives you Fe plus CO, because the pressure of carbon monoxide and carbon dioxide is more than 1 atmosphere. So the reaction moves forward. In this case, this won't happen because the carbon monoxide pressure is less, and at the same time, navim pentoxide doesn't become navim directly as written as the overall reaction. Say when you have carbon plus Nb2O5 in the phase diagram, you will be somewhere here, and then the reaction moves like this. It will go through all the paths. So actual reaction will occur in steps, and the carbon monoxide pressure, here it may be more than 1 atmosphere. Perhaps these two reactions can be carried out in atmosphere, but beyond that, it will be impossible to have it in atmospheric conditions. You have to apply vacuum. Anyone, by the way, from IMMT Bhubaneswar? Raise your hand.
Dr. Aarti, 2 minutes more.
Sir, then I'll conclude. So the idea was, you have to keep your eyes open. Means the many things which work under atmospheric conditions, they may not work. The things may be different under vacuum, and these metals are not so common metals. You have to be very clear that certain interventions you can do. You have to understand how why the chemical species behaves like this, and you attack the properties of behavior where you can improve it. Just I take this one. Yttrium oxide, rather any rare earth oxide is to be fluorinated for certain metal extractions. So this is the commercial practice, that you take the rare earth oxide, NH4HF2, you mix, and you do it at 300 degrees Celsius, heating it for 12 hours. But we studied this in this department, perhaps DTA is available. So it turns out that this reaction also occurs in steps. And what used to happen was that NH4HF2 used to evaporate. To prevent evaporation, this evaporates at say 150 degrees Celsius. So to prevent evaporation, you do either slow heating or you hold it for quite some time. So if you carry out the reaction in steps, or ensure that the oxide conversion has taken place, and then you heat, then the overall reaction will be quite fast. So just in 30 minutes, we were able to complete this. So as the time is up, I'll conclude, and with the permission of chair, if any questions are there, I'll be take.
2 questions. Any 2 questions?
Sir.
The extraction procedure, whatever you have discussed, suppose there are rock, suppose when you deal the industrial material, we are getting with the rock. From rock we will suppose
in any particular mineral these rare earth elements are occurring. Whether the extraction of these rare earth elements from those minerals are same as what you are discussing, or this is for some different?
Yeah, I'll tell that see, Ministry of Mines has come into this field, then the extraction and refining, what metallurgists say and what mineral people say, they are different. Mining people or other people, when they say extraction, they mean solvent extraction, and when a metallurgist say extraction, that is conversion from ore to metal in refined form, whatever is suitable for further alloy making. So this is one thing, and refining is conversion to metal for mining people, but for us refining is for the purification. So when you say extraction of rare earths from rocks, usually the rare earths are the percentage is quite less in ppm and all, so you have to remove the gangue material anyway. You crush, grind and leach and then do suppression, and you bring to some concentrated oxide or some carbonate, oxalate, simple compound like that, and then comes the conversion to metal part. Okay, I hope you are satisfied.
Sir, we were talking about pyrometallurgy, this niobium oxide and tantalum oxide. So, is it happening that carbothermic reduction is taking place to produce these two?
Yeah, actually, for niobium, the commercial method is aluminothermic reduction. Although it has recovery issues and all, carbothermic will be better anyway. But in carbothermy, in niobium pentoxide, there is a problem that it melts and corrodes the containers, and then segregation occurs. So it is not commercialized as I understand, but it can be done. Means industry, academia has to come up with proper processing, and that can be told to industry, and they can do. As far as tantalum is concerned, it's prepared by sodium reduction of K2TF7. Directly it gives capacitor grade tantalum. But Ta25 plus carbon means what you do is take tantalum pentoxide and tantalum carbide, mix them together and heat it under vacuum. That is practiced somewhere, I guess, in Clancy, somewhere in Europe. That is practiced. That can be done.
So, thank you, Dr. Alok Avasthi, sir. And then, thank you for your one more question. So, Mike Pascal.
Your kind permission, I think you have asked some question regarding the rare earth ore and all those things, how they occur, and wanted to go for treatment. See, the rare earth deposits associated with the hard rocks, either carbonatites or alkaline complexes, they are just like any other ore deposit. There the grade is around 1%, 1.4%, 1.5%. So you can treat it any kind of the metallic ore deposits. They occur in form of disseminated, it occurs in the form of veins, it occurs associated with the part of that. So what you have to do is basically entire metallized horizon, you take it as a ore depending upon what cut-off grade you choose. You define the definition of the ore on that basis. Once you take out that material, you have to go for all normal process of pressing, grinding, and doing something. Bringing to the slurry or maybe some roasting, whatever the process you want. There is nothing separate process. Only when we are dealing with the placer deposit, particularly separation from the monazite, there in that part the monazite has to be separated.
Okay.
Yeah.
Thank you so much, sir. Maybe more interaction can happen during the break times. And we thank Dr. Alok Avasthi for his wonderful presentation. Now, the chair will give a small memento to Dr. Alok Avasthi as an appreciation. The next presentation is by Professor K.K. Singh, Professor IIT BHU, on the topic of recycling of tantalum from waste capacitors, an effort to address the criticality. Professor K.K. Singh is an expert in extractive metallurgy and he is currently professor at Indian Institute of Technology, Varanasi. His core research area is e-waste recycling and extractive metallurgy in general. So he has successfully handled numerous international and national research projects, and his contributions have recognized with the ISTE National Award, Best Teacher Award, and invited panelist in India's Vaibhav Summit 2020. So we hand over the dais to Professor K.K. Singh. Sir, please try to adhere to the time of 15 minutes, sir.
Thank you so much. So basically we are working on the printed circuit board analysis recycling. And what we found after developing some process for gold, silver, copper and all that, we found that tantalum is somewhere neglected because of its very lean presence into the PCB. But printed circuit board of any electronics, it is house of as much as 60 elements. So sometimes people ask us, and industry also asks, why not you are offering the complete solution? So as I will join Dr. Avasti that we have very less number of real metallurgists who are working in extraction. This is the era of material science, and more material scientists are there everywhere. Very few departments are left with the core metallurgy. And we are thankful that our Pujaniya Malviya ji established the department at Varanasi, which was the first in metallurgy, and he tried to solve the industrial problem. So I'm coming to that. So printed circuit board need many people to work. Here some industries are also there. We have interacted with them and they are working on the lithium ion battery. So we thought, okay, now let us move to the tantalum, which is the rare metal, really critical, and you can see how it is critical. The story was not very clear, so we started to see from where tantalum is taking birth and where it is going. So we started material flow analysis before doing any technical thing. Okay, so this is about data about the e-waste. I am not going into that because time is less. So directly coming to that. These are simply data. I will come back again, but let me show this. So this is a supply chain of tantalum in which the primary production, right from the mines, it is taking place, and then after mining, tantalum oxide is handed over for the extraction. Then processing plants extract the tantalum. Dr. Avasti was telling about and tantalum. So after that, then intermediate products come, then finally finished product come, then consumer, and then end of the life. So this is the life cycle of tantalum. So if you see this tantalum, at mining stage, you can see it is only 0.0002%, 2 ppm to 10 ppm tantalum is only there in the ore. So it is very difficult to extract. Actually, rest of the things are impurities, or in some cases many other metals are there. So if integrated processes are there, that's fine. Otherwise, very problematic. But tantalum is so important because of its very high capacitance. So in all electronics now, it is whether it is just a number of 10 or 60 or 70, a large number of capacitors are being used, and that tantalum capacitor is taking lead into that. So if you see the usage of the tantalum capacitor, tantalum capacitor, it is accounting for more than 40%. Means 40% tantalum is going for production of tantalum capacitor, which is being used in the electronic industry. So if we are able to somehow recycle the printed circuit board, we are able to recover the 40% green source of the tantalum. I'm not talking about the properties. Okay, so now this market is growing with the 6% for the world, and now because of the semiconductor initiative in India, it is increasing with the 12%. So different category of tantalum is there. Now this one is the demand and supply. Data is a little bit older, but trend is the similar. So you can see the mine production and the demand. Demand is always more, gap is more. So to fill up this gap, recycling is important. If you see, quickly I am going to how capacitor is made. You can see that there is a tantalum electrode, blue color you can see, and the iron and nickel terminal is there, and it is covered with the epoxy resin, which is very hard, and it contains the silicon. The problem with the tantalum capacitor is that it is surrounded by the silica. Whenever you try to break it, all silica is going to join the tantalum and recycling becomes very, very difficult. So for a very clean recycling, because for the tantalum grade you have very pure tantalum is required. So we have to somehow remove the silica, which is the mold attached with the mold. Okay, so these are the product categories in which tantalum capacitor can be recovered. So you can see the desktop having more capacitors. So it is a large source, and then the notebook, then mobile phones and all that. Not very clear to me from here, but I am trying to catch all that. Okay, so objective was to, in this light of that, why tantalum recycling should be done. So resource is limited, imbalance demand and supply, and e-waste is piling up. So e-waste we are taking as a source and opportunity. Let us recycle that. This is already covered. And now if you see the tantalum production, but if you want to be one of the major electronics producer in-house, we have to have that. So we have to rely on the recycling only because our sources are not there. Recently there was one news, I am not aware how much it was there, the Satluj river having the tantalum presence. IIT Ropar have, some researchers group have reported that recently. We have to look into that. If it is the news and huge resources there, that is very good. I think deputy advisor is here, might be knowing how much reserve is there into that. Okay. So again, these are data I am skipping because time is less. So this one is very, very interesting material flow analysis. You can see how much waste we are generating. So at the mining stage, at the production, you can see the losses are there. It is going down. Then in the processing unit also, we having the losses. And then we are moving to the manufacturing, and we are more concerned about the capacitors. The figure you can see 4332, and that after the end of the life, all these are coming here, and discard is okay. So you can see a huge number is being discarded, 9495. So out of the production of 13,000, and you are discarding this one, so almost 70% is being discarded. Okay, and then the piled up stock at the top 8876, that is also gradually coming and joining that. So this is the picture says that why recycling is very important. So I'm skipping all this, lack of time. So what we did, we tried to choose the hydrometallurgy, which is widely used. So pyrometallurgy, we thought it is a little bit difficult because of the carbide problem and all that, and minerals also not very much available. So we choose this one. And we, you can see after the breaking of that, manual breaking we have to adopt, because now at this point of time I just want to share with you, we need every different kind of expertise, like the robotics as well, robotics and machine learning kind of thing also, to predict how much tantalum is there on the printed circuit board, and how to remove very specifically, very precisely, so that we can recycle. It is very much profitable business. We have established, we have our papers, tantalum recycling, if anybody is going to establish that, it is very much profitable. But the problem is that how to arrange the tantalum capacity. For each and every printed circuit board, if you have having just 10 grams or 15 grams of capacitor, and then out of that the percentage of tantalum is limited, how much huge number of printed circuit will be required to separate it. So it should be integrated in the recycler's facility, and for that a clear separation or disassembly is required. So what we did, little bit this, yeah. So there are two methods. Alkaline leaching is there, and through the alkaline leaching, we are able to recover around 70% of the tantalum only. But when you try to ignore that, okay, first we will leach the other metals which are available in the capacitor. For other metals, these metals are manganese, nickel, iron and silver. So we took another way and tried to dissolve all the metals and keep tantalum intact. So by that way, we choose the ignored that. I'm going a little bit fast. So even in the leaching, what I was talking, two methods we adopted, single and double. I'm directly going to the double. So we took hydrochloric acid and then nitric acid in two steps and try to leach all the metals. You can see manganese, silver, nickel, iron have joining the acid, the solution, but no tantalum is going into the solution. So tantalum is remain there in the residue. So that is the beauty of the process, that you take out all impurity. For the sake here we are considering this as an impurity, so we can remove all the metals and then tantalum from the residue we can later recover. So this already explained, I think. So these are the detailed data. I'm not going into that. So how different parameters are working, like the concentration or strength or solid liquid ratio, how it is impacting, all had been studied. So finally, a process, going to that. Okay. So yes. So we took the after the leaching all metals in the solution. 2 minutes only. Okay. So let me go to directly the flow sheet what we have developed instead of telling all the stories. So in the process what we developed after the pre-treatment, we took the leaching stage. Here you can see where the organic matter have already been removed, the region what I was talking surrounding the tantalum. So the organic matter which having the silver also. So organic matter and silver going through the leaching and cementation, and silver chloride precipitate will come out after the NaCl treatment. And then in the metal rich concentrate after the pre-treatment, that has been treated in two-way methods in which residue tantalum is coming, and then after the pregnant solution is treated with the solvent extraction, and then raffinate manganese is first going out, then nickel is there, and after the nickel is also along with the iron, and iron just simple processes are adding the lime into that and it precipitate out. So all together manganese, nickel, tantalum, silver all separates very nicely. So as far as concept wise, this process result we have already developed. Now we have to scale up. We are trying, and again the problem, I'm not blaming anybody, but we have to take care of only 2-3 people are there, and you have to take so many practical methods, and few students we have to carry out. So out of that we are trying to solve as much as, but this is a good thing that we are interacting with each other and our community is growing and we are helping each other. Recently I was very happy Dr. Vasti helped us at BRC. Usually BRC was not so approachable for people because it is protected area, but now they are open up and they are helping in. So our community is growing, and I am sure with cooperation with each other, we are going to solve this critical metal issue also. Thank you so much.
Thank you, Professor. Now, because of time constraint, only one question is allowed, and then one will be given in bonus.
This year, three molar I saw. We have seen 3 molar used for leaching. So what was the acid concentration of the leaching? Why you have used the science procedure? Very costly. You have to really get down to nickel and unique capacity. You are interested in making it nickel. Science procedure has
So, see,
the acidity of the solution was not the pH of the solution.
yeah, so whenever we are going for the acid leaching, we always have the option to recycle. So, acid using and throwing, that is not the purpose. But when we are recycling it, so it is not harmful in my opinion. And regarding the cyanides, because it has very high selectivity, other reagent also used, but cyanides having the very much high selectivity. Yeah, but all together so many metals are there. So we will try. That idea I will take and
Yeah, that can be done actually.
yeah, okay. Sure, we will try. Sir. Thank you so much for this idea. Thank you.
Last, any question? Yeah. Interact with Professor.
Yeah, very good presentation, sir. I just have one question. When you are leaching, you are doing two-stage acid leaching. It's just the tantalum which is not leached out. I thought all the heavy metals such as titanium, vanadium will also be present in the residue. So the final residue which you are preparing, or getting, will also have those impurities or like other byproducts. So how are you separating them out at the final stage?
Now, when you are starting with tantalum capacitor, so there is only, please take a look. So it is only the manganese, nickel, iron, tantalum and a little bit of silver that already have been separated during the pre-processing time. So no other metals is there in the tantalum capacitor. So there is no question for other metals.
Yeah. Short question, please. You can ask short question. You want it? No, it's okay. So thank you, Professor. First thing, I think you have presented very well recycling of tantalum with comprehensivity, and the importance of the topic lies in that all of us have seen the printed circuit boards and the size of the capacitor, and within that having very small amount of tantalum and capability to extract that is really appreciable. In addition to that, I am thankful to you for adhering to the time, and even more thankful that when I lifted the mic, you understood and you have seen towards me. So thank you for all. So big round of applause for as a token of appreciation, I would like to present a memento to Professor. Dr. Abin Masto. Dr. Masto is a chief scientist and professor at CSIR Sinfor, an institution he joined in 2005 following the completion of his PhD at Indian Agricultural Research Institute, where he was awarded the gold medal. He has also served as a visiting scientist at the Pacific Northwest National Laboratory in the USA. Dr. Masto's expertise focuses on the utilization of fly ash, biochar, and biomass applications and creative innovative fertilizers. Key achievement includes developing slow release fertilizers from coal wash reagents and mapping rare and critical elements in coal ash. He is highly recognized for his academic contributions. The hundreds of 100 papers and an H index of 43 and over 7,500 citations. He would be making the presentation on the topic coal as a potential raw material for critical minerals. So Dr. Abin Masto, please.
Yeah, sure. Yeah. From the CSIR Central Institute of Mining and Fuel Research. It's more than 75 years old institute, We give technological service for the entire spectrum of coal, starting from mining to coal washing, carbonization, combustion, and the environmental issues also. Of late, recently we started working on mapping critical mineral in the coal. Because you know, coal is a heterogeneous material. It contains almost all the elements of periodic table in different concentration. Obviously at very low concentration. Almost all the element of periodic table is available in the coal. Okay. So globally, recently if you see globally US or China, Russia, they identified coal and fly ash as a potential raw material for critical minerals. But in India we have limited information on the content of these critical minerals and rare earth in coal. Our data shows that the total RE concentration in coal can go up to 300 milligram per kg ppm. Some of the waste rocks in coal mines has more than 3000 ppm of rare earth elements, and till date we have come across 500 to even less than 600 ppm of rare earth elements in coal ash. But in lignite ash, the concentration is even up to 3000 ppm at Neyveli. And there are some studies by GSI, they say the germanium is 120 milligram per kg, lithium up to 250 ppm in some coal of WCL area. But unfortunately, we don't have any comprehensive database on the critical mineral content in the Indian coal. Recently, CMPD has started working on mapping the critical mineral in coal as well as the rocks associated with the coal mines. Okay, way back in 1935, a German paper in ACS, he has clearly mentioned that the percentage of rare earth elements in the coal ash could be sufficient to have an industrial recovery. Maybe probably after a century, maybe after 100 years, we are looking into that. Why the coal ash is important is some of the elements, their concentration is comparable with the ore concentration like scandium or gallium, but not necessarily the cutoff grade is equivalent to the ore concentration, because when we talk of ore, they are in hard rocks, a lot of investment is needed for mining, so the concentration needs to be higher for economical cutoff rates. But in fly ash, it's already in the powder form, even with the less concentration, it could be economically viable. Okay, quickly I'll go through what's the scenario with the different coal and coal products of India. The red lines are sandstone. In sandstone, the rare earth is not that very encouraging. And these black ones are coal. Obviously, it varies with the geological conditions of formation. And if you see the shales in coal mines, the rare earth concentration goes even up to 1500 ppm or even much higher than even the fly ash concentration in the shales. So before mining, whether we can isolate the shale and make it useful for rare earth extraction. Some of the heat affected rocks, that is the maybe the sandstone get converted due to the high temperature. There also some amount of rare earth is there. Then you see the jama, that is the heat affected coal, and these are the lambrophyring, that is the igneous intrusion into the coal seams. There the concentration is quite high. Not only rare earth, we have good amount of potash and magnesium also, both are critical for India. Okay, with this background, initially I will be talking on lithium and few critical elements in coal, then we'll have a detailed discussion on rare earth elements in coal and ash. We did a thorough mapping of lithium content in Indian coal. We did a project for CSIR, and we did mapping for all the coal fields of India, and we could get a maximum concentration of only 38. It's not very encouraging. The lithium content is too low because atomic number is also less, and but in some of the fly ash, the lithium content can go up to 127 ppm, but it's still far below the economic viability for extraction. We did the chemistries, what's the mode of occurrence of lithium in the coal. Most of these lithium is in the residual form. So though the concentration is less, but again it is with the hard matrix, it is very difficult to extract. Incidentally, we could identify some of mica mining bays that has appreciable amount of lithium in the Koderma area. This is a case with fly ash, JSW lignite based fly ash. They have the high amount of lithium. Again, when you talk of fly ash, even the boiler technology also affects the distribution of rare earth and the critical element in the ash. I'll come into that in this later. Coming to the rocks in coal field. because the OB material and the waste rocks also has lithium that we were expecting, but unfortunately we didn't get much concentration of lithium in the waste rocks. But we could get certain rocks with high amount of magnesium, potassium and phosphorus. These two are critical for India. And when I talk to my friends in Europe, they say they powder that such kind of rock and they sell them as a fertilizer because it's rich in potassium and magnesium that can go as a fertilizer. So that's a good scope for extracting potassium and magnesium from this rock, because if you see ECL area, there's a lot of huge thick blocks of igneous intrusion is there, basaltic layers are there. We can explore for potash and other minerals in that igneous intrusion. Okay, another interesting element is gallium. So we don't have any source in India. Our concentration is comparable or even slightly higher than the bauxite residues. So when we take the rare earth and other material from fly ash, can we go for a co-extraction of gallium from fly ash? Because the concentration sometimes it goes to 80, and we have seen some of the beneficiation, it can go up to 150 also. I have data, I will be presenting that. So gallium is another potentially important candidate for extraction from coal and coal ash. Okay, now the entire presentation will be on the rare earth elements in ash, because if it is present in coal, ultimately we have to extract from ash. When you combust the coal in the power plant, it gets concentrated because the ash content is 25 to 30%, so the concentration increased by 3 times when you burn coal in the power plant. Coming to a scenario of what we are doing with the ash, in the world we have 800 million tons of fly ash is generated. India around 300 million tons of fly ash is generated. So most of them are going in other say you can say most of them are dumped in a landfill or in a concrete. So the valuable critical minerals including rare earths are being dumped permanently. Okay, coming to what's the cutoff grade of fly ash to consider as a promising rare earth element, a rare earth source. In India we don't have any cutoff limits for fly ash. These are some Chinese literature. They say the total rare earth oxide should be around 1000 ppm, and the outlook coefficient, that is the ratio between the critical rare earth and the excessive rare earth, it should be at least 0.7 for a promising case, and if it is more than 2.4 it is a highly promising case. So that's two yardstick we are using to characterize the Indian fly ash. Okay, coming to methodology, we collected ash from different power plants across the country, and we did elemental analysis by following the ASTM protocol. And for data quality control, we use different certified reference material, including rare earth ores, and we are getting very good recovery for lithium metaboric based digestion, even with an ICP OES. And this is the critical and excessive, the ratio, if it is more than 0.7, this is considered as a promising source. Okay, this is a summary of total rare earth element present in the country. Say, starting from all these coal-based power plants, the concentration is less than 627 ppm, that is 1000 ppm in terms of rare earth oxides. And elemental concentration, it should be 627 as per the Chinese literature. And Barmer is again lignite, but the concentration is less. Other power plants also, it's somewhere vary between 400 to 550 ppm. But very interesting result in this Neyveli, we are getting up to even 3000 ppm of rare earth element. Again, there's a difference between mine 1 and mine 2. And within mine 2 also there are two power plant technology, one is 2000 and one is 2900. So the combustion technology also matters. When you do a low temperature combustion with a CFBC boiler, the rare earths are enriched. The concentration is very high and it's around 3000 ppm. Another intuition is probably this is due to the monocyte belt of this entire coastal area. That is the reason we are getting rare earth in the lignite. Why not in Barmer area? So it's a lignite, but there is not much rare earth in Barmer. Okay, for any industry to invest, there should be consistency in the data. It's not that okay, someday we got a good concentration, so we did a continuous evaluation for 7 days, and each day multiple samples were collected. See, good, the standard deviation is quite good, and you can see the data of the total rare earth is also consistent, so one can go for investment confidently with fly ash. And this is the Chinese yardstick. If you see, the promising case are only the neighborly lignite ashes. And all others are just near that. We can do some kind of beneficiation and take it into the promising zone. But as of time being, the neighborly lignite ash is not highly promising because it is less than 2.4. It's promising source. Okay, now let's see some difference in the chemistries of coal ash and lignite ash. Because the coal is a highly matured kind of fuel, but lignite is less matured, and these biomass and again this is sugarcane base, these are very low matured, we can say not at all matured. Coal ash is basically rich in aluminum, but lignite is rich in calcium. So the extraction strategy, leaching strategy will be different for coal ash and lignite ash. But for biomass, it is more of potash, and they are water soluble. It can be easily leached. So why I am presenting the biomass is once you remove the potash, almost 50% of the bulk material is out, and the rest residue is concentrated in rare earth as well as scandium. The distribution is fairly same across the different ashes. Critical and excessive distribution is fairly same for across the coal ash and lignite ash. Coming to the chemistries, what's the mode of occurrence? Whether it is in metal oxide bound or it is in mullite and quartz. If it is present in mullite and quartz, it's very difficult to extract. If it is in the metal oxide, we can easily extract. So if you see the coal ash, it's more of green lines, green color. Here it is more of ash, grey color. So lignite can be extracted easily with a mild acid condition itself. But for a coal ash, we need some harsh condition to extract to get the recovery from coal ash. Okay. This is what we did, the mode of occurrence, and these are the prominent elements. We have to go for co-extraction of aluminum, gallium and Nd, or potash, and scandium for biomass, or aluminum, zirconium also, almost 600-700 ppm in lignite, and we can talk of scandium also. Okay, coming to beneficiation, because the distribution in particle size is also good. In post particle, the outlook coefficient is very high. So what we suggest is, can we separate the coarse particle and go for rare earth extraction, and the rest can go for a landfill. We did some selective grinding for enrichment, but it didn't work. And size separation also we did for lignite ash as well as for density separation. Some elements are highly sensitive for density separation. And yeah, here it's interesting thing. This is the bulk ash. When you do this density fraction, some fraction the concentration has increased, but the outlet coefficient has decreased. I mean that light rare earth is increasing. Here also in size fraction, in the finer size fraction, the concentration is slightly increasing, but still we are compromising with the lighter rare earth. So based on that, we develop a small preliminary flow chart, go for a density fractionation. The heavier fraction, they are rich in iron oxide, titanium and gallium. Then the lighter fraction, we can go for particle size separation, go for RE extraction, and almost 50 to 60% of the bulk ash can be used for the routine cement and other concrete application. And we did some leaching also, and we could get almost 70% of extraction. And this is a tentative flow chart, and prepared RE concentrates of 6% REOs. And okay, what's the challenge is why we are unable to upscale it. There are few attempts at CSR, IMMT and ALCO is doing it. And recently there is an agreement between Neyveli Lignite Corporation and BARC for pilot demonstration. And in US there are a lot of pilot demonstrations starting from 2017-18. China, it's not available in the public literature, but there are some papers says they have pilot as well as commercial scale for gallium and germanium too. Okay, what's the challenge? What are the important takeaway we have to do for coal ash as a potential raw material? For one is ash beneficiation is needed. Then how we are going to do with the residues. 300 million tons fly ash is generated, and now the Ministry of Environment and Forests go for their stringent guidelines says 100% utilization. So if we use rare earth, then again we will get more than 100% of residues will get. Then competition with primary source, obviously of course not now, and the recovery percentage and all the process are at small scale, mostly in papers, and only 2 pilot scale facilities are coming up, and really we don't have any economic viability calculation. We have to go for co-extraction, that's very important. Maybe either go with gallium or alumina, or sulfur or plant nutrition, and interference for selective extraction. Yeah, finally co-extraction is very important. If it is biomass, then go for potash, alumina and rare earth elements. So with this, the main conclusion is, yes, now there are a lot of labs and institutes are working in isolation. We have to come together and work in a collaborative mode. As we know, India has a diverse geological formation, including significant igneous intrusion. So it could harbor varied amount of critical elements in the coal, and we have to focus on extracting base metals along with the REs like aluminum and potash or gallium. The extraction of critical metal for coal and mining base several advantages, because it's already powdered ore, powdered material is available. We need not to pulverize it, we need not to mine it. And if you see our conventional monazite based rare earth, it's radioactive, but our fly ash, the coal based material is not radioactive. So there's a lot of advantage to go for fly ash, and before that we need to go for a detailed mapping and what's the sampling strategy so that the data generator is consistency. So with this, I thank the audience and thank the organizer. Thank you.
Thank you, Dr. Ebin Master. Any questions?
A very good data also you have presented. We need such type of the work. I don't have any question, but rather I have a small suggestion. One very important element which you can look in this is germanium. What happens that germanium you will get not made with the coal, but germanium will get adjoining non-coal rock, that is mainly shelly horizon or maybe some silt horizon. If you have a access to those coal deposits, please try to do some sampling, analyze germanium. Some of the coal areas where data is available, it gives more than 200-250 ppm of germanium, which will be a very potential critical mineral.
Yes, sir, I agree, because we have some germanium data, but still I need to validate that. I'm getting more than 100 ppm. That's why I deliberately removed that. We want to validate the data before bringing it.
Some of the coal areas, particularly in Jammu and those areas, germanium is reported very high.
Yes.
I have two questions, very small questions. You have shown the distribution of RE, different types of coal. You have mentioned the sales also that contains rare earths. I think 1,500 you have shown. But the dike also has been analyzed for that.
Yes, sir, the two igneous rocks I have shown there.
You have not shown any data on that. So please you include the data on dike also. And another thing, this Niveli, where the rare earth concentration is 2,800 ppm or near about 3,000 ppm. So what was the concentration? What is the concentration of lutetium? You are showing in one of the slides that is 1 or 2 ppm, like that. And then again you are giving some outlook coefficient that where you are showing that it is in excess. So these two things are contradictory. So can you just explain about these things?
Okay, sir, what's the maybe I didn't give the entire data profile. I'll check it, sir. I'll check it. But the outlook coefficient is around 2 inch coming.
Last question, please.
Sir, just small question. That is 3,000 ppm.
Sir.
NDDM plus it is.
So we visited last year. That is particularly TS2 expansion. There are many boilers to go to TS2, but now we don't have access because BARC into that, because maybe in this forum, I don't know, if we can give access for us also. Now BARC has come in, so Niveli is not giving the samples to us.
Yes. Yeah, last question by Sharon.
One aspect actually. One of the slides you are mentioning that gallium fly ash is the only source. But I beg to differ on that because aluminium industry is a bauxite, they have huge resources. And they have kept it under the carpet.
Yes, sir. Because I know that from the bauxite facility they are doing it, but now they stopped the extraction. What I said is this concentration is comparable with the bauxite facility.
Yeah, we thank Dr. Ebin Master for his insightful presentation and very highly informative, sir. The other questions may be addressed during the tea time. Now, as a moment, as an appreciation, so we would like to present a small memento to you, sir. Our chair presents that to you. So now we move on to the fourth presentation of this session by Dr. Kumari Yadav, Scientific Officer, BAG, Mumbai, on the topic of scalable next generation hydrometallurgy process development for rare earth extraction and end of life NdFeB magnets. So Dr. Kumari Yadav has joined rare earths development section of the materials group at BARC in 2007, holds a PhD in chemical sciences from Homi Bhabha National Institute. He is an expert in the separation and purification of critically important elements like rare earth, base metals from diverse sources. Dr. Yadav pioneered in development of successful technology transfer to IREL of a process for REE recycling from NdFeB magnetic scrap, achieving over 95% recovery. He also advanced novel processes using PES beads, membrane-based recovery for REEs from lean streams, IREL plant effluents, etc. So he is the recipient of Department of Atomic Energy's Young Applied Scientist Award and Group Achievement Award. So Dr. Kartikeya, the dais is yours. So please adhere to the time. You are given with 15 minutes of time. Thank you.
Thank you very much for the kind introduction. So my name is Dr. Kumari Yadav. I am from Bhabha Atomic Research Center. And today I am going to talk about scalable next generation hydrometallurgical process development for rare earth recovery from end of life magnetic scrap. I am working in the field of hydrometallurgy for last 18 years. And to begin with, I wish to thank Dr. D.K. Singh for inviting me. He is my guru in this field, in hydrometallurgy. And hydrometallurgy is not given the due importance or priority as I feel today. Even most of the cases it has been known as or told as bucket chemistry. But this myth, I want to start my presentation by breaking this myth only. So in periodic table, we have almost 80 stable elements. धरती पे 80 stable element मिलते हैं. Out of those 80 elements, around 10 are gases, 2 are liquid at the room temperature, which left us with around 68 elements. Out of these 68 elements, 50 elements cannot be separated if there would not have been hydrometallurgical process at industrial level. So 50 elements can only be separated by hydrometallurgy. So in this, I am talking about the group of elements, that is rare earth element, which is most difficult to separate from one another. And only one and only hydrometallurgical processing can do this. Even yesterday evening, Saraswat Saab is also telling that we need to develop expertise in the field of hydrometallurgy and in solvent extraction just to solve these problems. I am a chemist. I did my MSc in chemistry followed by PhD, and I can tell you there is no more difficult problem than separating individual rare earth, sister rare earth element from one another, like NdPr, which requires 100 stages of front extraction. So leaving from this discussion, I am going to talk about these rare earth elements. Now why these rare earth elements are important? Why they are used in so many fields? What gives them that property? And that property comes from their 4f orbital electrons. The valence shell configuration, last electron goes into 4f orbitals, which is shielded by 5d and 6s orbitals. And because of that, they retain their chemical properties. Properties like magnetic property, luminescent property, electrical property and catalytic property. As they retain their property, no matter in what phase they are present, they show that property, magnetic property. Like most strongest magnet is made by rare earth element only. Now this comes at what are the fields, what are the areas where these rare earth elements are used. Actually this has been discussed many times at this forum, so I will skip this. But basically it is used for magnetic, glass polishing, catalyst, phosphorus and many other fields. And one key aspect I want to highlight here, that for all these applications you have to separate and purify individual rare earth more than 3,9 purity. 99.9% pure rare earth element is required. And one key aspect where we are going to discuss is magnetism. Rare earth based permanent magnets. How important they are. Why they have become so much important. So this dark portion of my slide represents the magnetic properties, magnetic energy, MgOe, which is being told as the magnetic property of the material. If you can see the bottom one, which is oligomagnet, it has around 5.5 MgOe. Say it is a parameter to measure the magnetism of that material. Exactly 10 times more is NdFeB, rare earth based magnet. Nd, iron boron magnet have more than 10 times magnetic field energy or energy product. So they have very high magnetic property, which enable us to use that magnet even or reduce the size of the magnet for our application. And because of these only, the modern day application like hard disk drive, electronic consumer item, windmills, and so many other applications have come up, and we are using nowadays. Now I want to compare this with primary resources. Say I want Nd to I want 1000 kilogram of Nd from my primary source. If I want to separate it from monazite, beach sand mineral is an Indian ore which contains around 0.1%. Actually, this is a good estimate. It contains less than 0.1% of monazite in beach sand mineral. In that 0.1% of monazite, around 60% is rare earth. In that 60% of rare earth, some Nd is present. So for 1000 kilogram of Nd to separate, we have to take care of 1000 kilogram of thorium in our beach sand mineral. Say I have some another monazite source which is basically not present in India, but other type also contains around 50% of that amount, the radioactivity, which is thorium. So for 1000 kg you need 500, you have to separate 500 kgs of thorium. The last carbonatite of ore that contains a small amount of thorium. One problem. Another problem, say I have to separate 45 grams of dysprosium, an important ingredient of making a magnet. So for that I have to mine 1000 tons of beach sand mineral, process it, and then only I will get that 45 grams of dysprosium which is present in our Indian ore or monazite. Now let us compare this with a secondary source. Say I have an end of life magnetic hard disk. That hard disk drive contains NdFeB magnet. That NdFeB magnet contains 30% of rare earth. Highlighted in pink color, I guess this is pink, no? Pink color. And if you compare with the primary resource, that contains only 0.03 or 02% of Nd. So here starting material itself is 30%. So if I can develop a process, we have a source with us only, and that source is 300 times more in quantity if I compare with my primary source. So we at BARC, we have developed a process. Why recycling is important for rare earth element? If we see the scenario worldwide, rare earth element, last corner of this slide, rare earth element, only 0.2% of rare earth elements are recycled. Everything else is recycled more, reused more. Partly reasoning maybe many things are coming to end of the life today, and secondly the reason is the main player in recycling is China only, from where we don't have data. But this does not deny the fact that India is the second largest consumer of electronic goods. So we are the biggest generator of e-waste in the world. So we have the biggest resource of these rare earth elements with us only, which we are not able to recycle it or reuse it, or we are able to reprocess it. And for that purpose only, at BARC we have started this work in 2015, where a simple hard disk drive we have taken the magnet out of it in just next to the reader. This is the magnetic piece. It's a very strong magnet. We demagnetize it with thermal demagnetization, powdered it, followed by hydrometallurgical processing, and then ultimately separated rare earth oxide. Rare earth oxide as a product which has greater than 99% purity, but it was mixed rare earth oxide. It contained all the rare earths which were used to make the magnet, that is Nd, Pr, Dy and Tb. So 4 rare earth elements were present. This we have separated. This technology we have transferred to, these are the steps. This technology we have transferred to IREL, and this technology has been showcased as a technology demonstration plant at rare earth and titanium theme park at Bhopal. Demo runs have also completed. At 10 kg scale we have showcased the technology transfer has also been done, and this is the leaching step for 10 kilogram scale of NdFeB magnet leaching step. At the end of this process, we could separate the mixed rare earth oxide at the center, mixed rare earth product which contains Nd, Pr and Dy. Now the addition of Dy creates two problems. One, the product is subpar, Nd, Pr, Dy mixture. So we have to either remove the Dy because Dy is costly, it is around $500 per kg, and also it is actually reducing the purity of my product, and for that we have to see the option. The difficulty was Dy content varies from magnet to magnet, so scrap to scrap. It means our product, what final product we are getting, which originated from different type of scrap, contains a range of dysprosium. So for that, conventional processes like solvent extraction, ion exchange could not work very good, because in some lots I was getting less than 100 ppm of Dy. Separating them by condensation process is never be economical. So we developed the processes. This was a part of my PhD work also. So some resin we have developed, and I can tell you that this resin was actually scaled up to a scale where it can remove some meaningful amount of rare earth compounds. Sir, how much time remaining, sir? So I will not go into the scientific part, but I will just showcase what technology we have developed. So we wanted to develop a polymeric composite beads which should have the advantages of solvent extraction and ion exchange. Ion exchange has advantage of solid matrix. Solvent extraction has advantage of bulk extraction. It can extract a lot. So what we have done, we have created a cavity, and inside that central cavity we have fed our organic extractant, and now this is being polymeric bead. So the central portion is filled with that organic solvent, and this is porous in nature. So this bead we just, this portion I will not, this is the developmental data. Only thing what I wanted to do, tell you that Kd values were initially 10. Kd values are the measure how much metal of interest we are extracting. So we started from 10, we modified our polymeric bead, and we reached up to 50. 50 is the benchmark. Beyond 50 it can be industrially scaled up. Different type of polymeric beads we have made. We have done all the scientific data. This was good work, so it got publication in good. This plot is important. This plot tells us there is no chemical interaction between polymer and extractant. Means extractant retains its property, so it can be as it is used inside the polymeric beads. We have checked the stability also. It was stable for larger amount. This was my first plant scale run, where at 1 kg scale, what I have done, we have taken a solution of actual magnet which contained Nd, Pr and Dy. Nd, Pr was around in gram per liter, Dy was around 100 ppm only. These polymeric beads can extract all the Dy out of it, make the Dy below reduction limit, and we could separate high value dysprosium from our NdPr product. This NdPr now can directly be converted to fluoride, subsequently to metal, and can be used into formation of magnets. And this is the setup which we have installed in IREL titanium theme park in Bhopal, and this is the method of synthesis of polymeric bead. This can be used up to 200 cycles of operation without degradation of extraction efficiency less than 5%. These are some advantages: conceptualization of the work, transfer of the technology, and finally demonstration run. All the steps have been covered till today. And as yesterday Saraswat Saab was talking about cobalt nickel, in VRC we have this expertise of developing hydrometallurgical process not only at lab scale but to up to plant scale. One example, Marajing steel is available with Midhani, which contains 12% of cobalt, 18% of nickel. In India we don't have any primary resource of neither cobalt nor nickel. We have developed the process for that steel scrap from lab to plant scale, and we could develop it at kg scale. Now heavy water board, a subunit of Department of Atomic Energy, has set up a pilot plant at 10 kg scale. Subsequently they are going for 250 tons per annum plant capacity. This technology has also been transferred. So with this I just want to highlight that VRC is trying to do its bit in the field of hydrometallurgy with the cooperation of all the concerned parties. Thank you very much for the kind attention.
Any question, please? Okay, so
it is a very nice presentation, Dr. Ritesh. I just want to know that how we can ensure the supply of raw material availability regarding spent NDFEB magnet. Because for wind turbine industry, there was a big magnet, but how we can ensure about the PCB or computer scrap magnets?
Okay. So in this irony also I want to highlight it. When I started this work in 2016, we in BRC only scrap around 1000 computers per annum. So the problem of scrap for us was not difficult. At that time I checked the market also. Market was also quite favorable. All the scrap dealers contain this type of magnet. Cost was only 500 rupees per kg for the scrap magnet. Somehow, with passing time, say today, you cannot get a magnet in the scrap market.
Yes, that is true.
Why you cannot get? Because the proper syndicate is there that is exporting all the scrap magnet. They know that now we are going to do it. So if this scrap magnet is available, it is the best source. We are the best producer of that scrap. We can get all the value out of it. So magnet is actually wiped out from the market. Now it is even costlier than the ND product itself. Say you are separating ND, it will be costly than the scrap itself. So somebody is buying that costly scrap, which is not meant for use for them also, just buying that so that we cannot scale it up. But I think that at government sector or at university scale, there is a lot of scrap which is being generated. They can in-house develop that demo setups, and this will help at the next level. Industry also can come and see the feasibility. Once it is diluted, then I think we can compete with them. And now ND cost is also increased, so it has become competitive.
Thank you. Thank you, sir.
See, the question is, what you are saying, probably it has been sent outside the country. Are you sure it is being sent outside the country?
Sir.
Then why not some efforts have been made to stop this type of this export? Who has given? The government of India come very heavily for such type of the things, because basically if the technology is developed, it becomes a potential resource.
As teaching sir told, our NDPR requirement is also not very high.
I'll answer that. See, actually the export was taking place, but when this facility came, then the contacts were developed with that gentleman. The export was taking place from Punjab. So then he was attracted to get it done here in India itself by showing him the facility. Then that gentleman attended our program at Bhubaneswar, also in Bhopal, and I think now is he coming to Bhopal for this? So probably he is coming. But this problem what Madam has highlighted is a real problem, because you know that waste, of course, we have a large population, the usage of material is very high, but at the same time we have the tendency to preserve. Like iPhone, life is 4 years, but still you will find many people have iPhone 7 running successfully. So our preservation is also a impediment for this collection of wastage. But ultimately, the question is that, see, feed problem comes where you have a running plant. But this is a technology which has been developed, and this is a solution proposed. So once that situation will arise, necessity will arise, obviously we'll get the feed also, because we know what could be the source of the feed. And as far as what he has answered was basically the tendency which is taking place continuously and consistently at the global marketplace. But when somebody is responding that, it doesn't mean that he has seen it, or he has witnessed it, or he has the source to stop that. So that's my limited submission. So with this excellent presentation.
Sir, one last question. What about magnet scraps which have like rust in it? Did you use those magnets as well, sir? And what was the quality or the difference in the quality?
So the basic advantage with hydrometallurgical processes is that you are going to leach everything into the solution. So rusting the rusting of magnet is not a problem as far as if you have sorted it properly. Rusted magnet dissolution is not a problem, because in our process we are purposely adding some nitric acid. Now nitric acid being as an oxidizing agent, actually it can dissolve all the rusted type of magnet also. So there was no residue. Only problem with these type of magnetic scrap is mixing with other things. So sorting should be done at very first level itself, when scrap is being generated. If it is being mixed, then it will be lost. Otherwise, rusted, corroded, or say powdered magnet, that is also not a problem for this process.
And are you also breaking them down into individual oxides or just NdPr oxide?
Actually, NdPr is an individual oxide. NdPr need not to be separated if you want it for a magnet application. One thing. Apart from NdPr, dysprosium and terbium is present there, that we are separating.
You're separating.
And that is why the value of NdPr is increasing in our product.
So practical demonstration can also be seen in the plant. There is working plant that is under technology development. Sorry, I think no more question because we are running out of the time. Excellent presentation, Dr. Yadav, and I could see your deep diving into the subject. The subject was not so vast, but you have presented it very well, and every aspect you have covered nicely. So a big round of applause for and as a token of appreciation on behalf of our organizer, I'd like to present a memento to you. So next presentation is by Dr. Vishnu from assistant professor from IIT Kanpur. He is an assistant professor in Department of Material Science and Engineering at IIT Kanpur, where he also directs the Material Recycling Laboratory, specializing in materials recycling and non-ferrous extractive metallurgy. He holds a PhD from IIT BHU Varanasi. His significant research achievement focused on developing circular economy solutions for critical waste streams, including the recycling of end-of-life photovoltaic modules, the recovery of metal from spent batteries, and the valorization of aluminum straws into valuable product like hydrogen. So, Dr. Vishnu would be presenting on the topic of material recycling pathways towards circular economy of critical metals. So, hand over to
Namaskar sabhi ko. Mera naam Pranav. I am faculty in the Material Sciences Engineering Department at IIT Kanpur, and I am going to present on materials recycling pathways towards circular economy of critical metals. CRISP CRISP 2025 is on critical metals. So this presentation is basically a generalized outline of what pathways really mean, what materials pathways really mean, what energy, how energy really comes up into this picture, and what we are trying to do in our laboratory. So, next slide please. Next slide please. So when we open up in this slide in the classroom, this is one of my standards class slides. We have this three E's of recycling, which is somewhat different to the R's of recycling. And when we become E's, we have engineering, efficiency, and economics. So we ask very general questions to the students like, what are the industrial perspectives of any material process that we have? Then we have the efficiency of the process. What is the process efficiency that we have, let's say, studied in the class? And similarly, what is the process economics? Now, in this session itself, we have seen the presentations by, let's say, processing and Dr. Yadav, who has just presented just before me. They've been talking about base-printed circuit boards and NdFeB magnets, and we have seen so many good material processing flow sheets. Flow sheets really help us to answer these questions. Let's say, what is the industrial perspective? So, most of the processes that we have now experienced in today's presentations as of yet have some industrial acceptance.
Of course, it would be a bit more of a challenge that how would these be translated from a pilot scale to an industrial scale, and how TIL levels really shifts. What is the process efficiency? In a lab scale, when we ourselves are performing experiments on a lab scale, we would like to have, let's say, an approximate target of efficiency of, let's say, at least 80%, and going above 90, maybe 95, depending on what is the raw material, what is the process efficiency, what are the process parameters, and so on and so forth. And comes the process economics. This is generally something that students really are not able to project, and we at MRL are trying to answer this question, because at academic level, this is this strong question that we are asked, and what are the real profits that we can make. So we would like to see how materials that we add, let's say in a lab scale process, how do these move, and how are these converted into products of our interest. Let's say each liquor converting into various precipitate, 1, 2, 3, depending on what we are adding, and then if or not we are going into solvent extraction, or either way, in the end, if we are going into electrowinning. Now, critical metals. This type of slides have been so many times discussed. We have DY, COs, GA, IR, NE, TB, and so many different metals based on different types of criticalities. And the factors that usually make them critical are the natural abundance, the applications, and the cost. This has already been discussed. What we really want to think is, we have a raw material. It could be a primary source or it could be a secondary source, and with this we perform pre-treatments, and then there's the set of activities that we can do. Let's say I come from a group of hydrometallurgy, so I'd like to stick towards the leaching and the precipitation aspects, and then we could go into the refining of products based on what type of products we want. Most of the times we would like to go into final metals, but at times it is easier, and I'd just like to put it that way, it's sometimes easier to make metal compounds and see if it could be marketed and if it has the applications in certain areas. So material, pre-treatment stage 1, stage 2, recycling processes stage 1, stage 2, and then there could be a third level also if we want to make metals per se, refining stage 1, stage 2. And these are the common processes that usually are present: comminution, heavy media separation, magnetic separation, gravity separation. One of the new aspects that we have used, and in addition to the REE recovery that we have tried in our lab, is something called alkaline roasting. We try to recover it from fluorescent lamps. So one of my students was able to incorporate alkaline roasting, which was basically she tried to grind KOH and NaOH in different batches and try to mix the fluorescent powder and recover cerium. She tried to recover, her target element was cerium. So this type of activities we would like to do and recover some metals from of critical nature out through the process. So, and why is this so important? So raw feed is something that we start with, let's say in this case, and something that I'll be discussing is lithium-ion batteries. So we start with lithium-ion batteries and CO types. We first perform the discharging, dismantling, and then we get the first black mass, and then the black mass we go for the actual recycling through the hydrometallurgy. This is something that has been performed by one of my students, Siddhant, which is basically 2 molar leaching H2SO4 with H2O2, 30% H2O2 addition, and this is on of various time frames from 30 minutes to 180 minutes. We see that with 2 molar H2SO4, we are about to reach near completion lithium recovery. So again, this is only with the addition of H2O2. Without the addition of H2O2, it cut-offs around 60%. Similarly, we try to do it with HCl as well. This one was without H2O2, and some were able to reach a maximum of 95% after, and again, this is 2 molar. after 180 minutes of time. This is something new that we try to do. So apart from the experimental data, which is pretty much common with every researcher group, we try to put it in various AI ML models. So what we see here is something that we predicted through models and something that we got through actual experimentations. It has a nearly around 2 to 14% of difference in terms of various parameters that we could identify. This is basically due to overfitting of the data that we had. And how do we really do it? We collect data from various literature information that is already available with us. We try to pool up the data and make a master data bank, and then we try to compare our data compared with the original data that is available in literature, and then we see some sort of gaps. This is what we are achieving as of yet. So from our side, this is the first ever steps of including extractive metallurgy and machine learning into the same pool and see if we can do something meaningful out of it. Similarly, for the case of HCl, just like H2SO4, collecting data from H2SO4, we did the same thing, and similarly for HCl, we see that we have, in case of HCl, we have 5 to 11% of variation of data from with respect to the data available in the literature and the data that we have just shown. In the previous slide also, there is something called heat maps. This is very crucial when we talk about machine learning data. This is very crucial. If we see that lithium recovery is dependent heavily on acid concentration, similarly time and temperature. This is something that is very much predictable just by, if somebody is very good at hydrometallurgy, they can directly predict. But what is the interdependence in terms of numbers, rough numbers? These models can really help us zone down these values. Similarly, if you look at HCl, it is around 50% dependence on acid, and then 25 odd percentage dependent on time, and similarly the temperature. What we see here is a general outlook, because I have always focused in this presentation on material flow, so I'm just putting up a slide for WPCB for rare earth recoveries. So all types of dismantling, shredding operations are done. We have the processes that we had previously mentioned about gravity separation, eddy current separation, and finally what we get is rare earth elements at the end. And of course, the metals of our interest has always been copper. In WPCBs, our primary target has always been copper, and then comes the other set of elements after the recovery of the base metals. So this is possible when we are primarily focusing on the sorting. The question that was asked just before this presentation was, how is it so important that magnets are, whether magnets would really give us good quality products or not, or whether sorting is important. Sorting is of course one of the most crucial parts that are preceding any type of flow sheet. The flow sheet only begins when we have a good raw material to begin with, just similar to PCBs that we have here. And next slide please. Next slide. Yes. So just similar to the PCBs, we have the flow sheet of LIBs as well. Again, discharging, drying, dismantling, this the students have already done. And we are able to separate out the cathode black mass, and the black mass that we had specifically used in our work was basically LCO type. And we are now trying to go into LFP also, but right now we have concentrated our work on LCO, and we get our material for lithium and cobalt. Similarly, if we try to use some pyrometallurgical route, we would also get the recovered metals in the form of iron, cobalt, nickel, manganese, and the LCO would be giving us the lithium in the recovered form. And I'd like to conclude in this presentation by saying that we have various flow sheets in different aspects. Let's say solar panels, we have lithium-ion batteries, we have waste-printed circuit boards, and different sources of e-waste. What is important is what are we targeting to recover, and what are the sort of surrounding elements that can be recovered in the process itself. So many times people consider it as a hurdle, as if let's say lithium is my primary target and I just want to target that only. It so happens that if we are designing our routes in such a way that we can incorporate every metal at the same time, we would be able to recover better. So designing of material flow is very important, which would be done when we have some good idea about the experimental data, as well as if it's our humble beginning that we are trying to bring in AI/ML also, so as to see if it really helps us to reduce some of the experimental work and directly predict some good experimental routes, so that we can directly zone into those aspects of material recovery. With inclusion of critical metals into modern material flows, material recovery has become dependent on the choice of unit processes followed. So,
this last minute.
yes. So we have to really choose which element we are wanting to recover and how we would like to proceed. This is what I have been discussing. And REE and LI I've just tried to explain in this presentation. Development of newer pathways for materials or material flows is an important segment for exploration of future. Thank you so much.
Thank you. Any question? Next side. Yeah. Dr. Aarti. Mike, this side.
Sir, I can. Which one, sir? Which one?
Okay. This table you are showing by machine language and AI, means you are trying to train. Now you have four variables.
4 variables, no sir, 3. The third one is basically lithium is actually the output.
Yeah. Say, how about your contact time and so many other things can be there, which
Yes,
are
yes,
not coming. And if you are training AI like this, then AI may give
which is what we are trying to say, sir. What we have right now is a pool of, let's say, 200 data points only. 200 data points does not give any much justice towards the whole pool of.
But at the same time, you are, I guess, you're considering that point of contact and all may not matter. Only 3 variables are there. Other things may not matter. Means other variables you are.
Right now, we have not considered them as an important factor. Of course, when it becomes, of course, the grid will further increase, and the R square that we are getting, let's say it's right now it's 0.7 only. Generally speaking, when we are looking at machine learning and AI heat maps, a general output would have been should have an R square of nearly about 95.95. So right now this result is very rudimentary to begin with. Sir, I have also 1 or 2 questions, sir. Yes. 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 Yes.
From the literature.
Yes. So
whether you have validated.
This is the data that we have generated.
Okay.
And what we got was a set of 200 data points.
What is the overall recovery?
Yes.
Okay. Of errors. I think in your initial slides you have also highlighted that you have done some work on phosphorus lighting devices.
Yes.
So here must be there many important errors are there. European.
Yes.
So at what scale you have done the experiment?
Right now, the fluorescent fluorescent lamp work that we had done was basically on the scales of grams only. So
how many grams is causing also?
No, sir. So that would have that is very well within 50 grams. very well within 50 minutes.
How you have taken care of the hazardous mercury vapor?
That right now, the student was just trying to dismantle the fluorescent lamp.
Not good. Like, that's what I was asking.
In a very
the student with this hazardous by now.
Yeah. So
must have the proper facility to treat all these things.
So this was done actually outside the lab only, just to ensure safety.
So, okay. So, thank you, Dr. And excellent presentation. I think you have, in the circular economy, through your work, you have tried to imbibe the analytics, and there is a good beginning. And I could find the correlation factor of 0.73 that itself indicates it's a quite means nascent or rudimentary, which you have also explained. So very well presented, and a big round of applause to Dr. Aruna. As a token of appreciation on behalf of organization, a memento will be presented to you. We are concluding this session with this presentation, and as you can see in this session, this was totally devoted to recycling. So there was a presentation on pyrometallurgy and rest were on the recycling. So overall it was very vibrant session. The speakers could keep the audience attentive, and also the best thing was that everyone has adhered to the time and we could finish the session well in time. Thank you very much to audience for all cooperation. Thanks.
Speakers for the insightful talks and well-structured presentation. And we also thank the chair and co-chair for guiding this session in a very structured manner. May I now request Professor Shatrughan Sore to felicitate the session chair with mementos from CRISP 2025.
Thank you, sir. We will now move ahead to the poster sessions. I humbly request the dignitaries to grace the plethora of posters displayed outside and move on for a tea break after that. We will commence the next session in 25 minutes.